Next, we're going to hear from Magda Moses, KM4EGE, and she's going to talk about observations and modeling studies of effects of the 2017 solar eclipse on SuperDARN HF propagation. This should be very interesting. SuperDARN is a very good system for making remote sensing measurements of the ionosphere and its connection to space. So take it away, Magda.
So yeah, as Daniel mentioned, my talk is kind of departs from, like, called it focused talks, but it is a system because it looks at HF that could be compared, whose data could be used with ham data. So, and we've got some talks about the next eclipse coming up after mine, so it might be good to look back on what we've learned from the last one. So just a reminder, the 2017 eclipse, as you probably all remember, crossed the entire country and started in Oregon and exited in South Carolina. One thing I want to point out on this map is that even though the path was pretty narrow of totality, the eclipse was most of the continental United States was in about at least 60% obscuration. So you can still see some good effects, some interesting ionospheric effects even in the partial region. So what we expected before the eclipse was that at low altitudes, where it's like the D layer, which are only really sustained by sunlight, the plasma would completely disappear. But at high altitudes, the plasma would be depleted but remain. And we expected also the plasma motion would play an important role in evolution, especially because we're at mid-latitudes. And of course, any change in propagation and change in the ionosphere can usually be detected by changes in radio propagation through the eclipse region. So this talk focuses specifically on like SuperDARN radar's data. So SuperDARN, or Super Dual Aurora Radar Network, it was originally just a polar network in the name of in the Aurora region, but it was so useful that it was expanded to mid-latitudes, and we have several in the United States. All the radars in this talk have each radar site this talk has actually two radars, an eastward and a westward looking radar, and they operate independently of each other, as shown in the top left figure. And that's the top left figure is a aerial photograph of the Fort Hays radar in Kansas. And yeah, you can see the supports. You can't really see the antennas running between them, but but the antennas can be phased from phased array to form a beam in a given azimuth, or in the direction of a given azimuth, as shown. So in the right figure, you can see the beams comprising the field of view of each radar, another site, Christmas Valley. So it's important to note that each radar can only make an observation along one beam at a given time. So you sort of have to choose your look directions and cycle around. But along each beam, not looking at the bottom plot, along each beam there's a wide elevation spread, and the radar operates at HF frequencies. Actually, it was at about 10.5 megahertz during the eclipse, and it can, sends out a pulse, and the pulse or signal can either be reflected from a large scale plasma irregularity along a field line, directly back to the radar. This is referred to as ionospheric scatter, or it can be go up and be reflected or refracted in the ionosphere, reach the ground and be reflected back to the radar from the ground. That's known as ground scatter. And it's important, we can differentiate, the radars measure not just the distance of that the scatter traveled, or that the signal traveled, but also they can measure line of sight Doppler velocity, as well as, well, some of them can measure the elevation angle of received scatter. As you can see in the top, if you look at the top left figure, the 2 antenna arrays. And the velocity information particularly can be used to differentiate what is ground scatter and what's ionospheric scatter, which is useful to determine whether any irregularities were forming during the eclipse. Now, specifically, we used these 4 radars in the eclipse experiment, mainly because they had fields of view that intersected the path of totality. So as you can see, this path of totality passed so close to the radars that the radio signals were likely passing through a partial eclipse region when they actually were in the ionosphere. But it was good enough. So also I want to draw your attention to the highlighted beams. So as I mentioned before, the radar can only make measurements along one beam at a time, but with the eclipse being only a few minutes, well, at totality being only a few minutes, we kind of want to maximize the collection. So we only used about half of the beams at each radar, and those are highlighted. And then we also had a camping beam, which basically between any 2 measurements on any 2 beams, it would return to the camping beam. So the beams, and those are highlighted in blue, and they have the best resolution out of all of the beams data. And those are what I'm going to, the data from those is what I'm going to show next. All right, so it's a lot of information, but each of the figures is a different radar, and they're all from the data from the camping beams. You can do the annotation. Oops, no. No, I guess I can't figure that out now. Okay, well, at the top, okay, no, here it is. So this panel, I want to draw your attention to like this panel here, that just shows the distance of the center of the eclipse from the radar. And over time, oops, what? Sorry. Okay. Sorry, technical difficulties. Sorry. So this panel here, that's the one that shows the distance of the eclipse from the radar, the eclipse center from the radar as a function of time. So it's just a proxy for the magnitude of the eclipse at each site. And the bottom 3 panels have x-axis in UT, universal time, and the y-axis is range of the scatter at which the scatter is reflected back. And the colors differ between the 3 plots. The top one is just the received signal to noise ratio, and the middle one is the velocity, the Doppler velocity, and the bottom is spectral width, which, I mean, so the important thing about the bottom 2 panels for each of the sites is that the velocities and the spectral widths are low. Therefore, we categorize that as ground scatter. So no, we don't observe any irregularities forming in the ionosphere during the eclipse, any large scale plasma blobs or anything like that. So now just looking at the signal to noise ratios and comparing the different plots. Well, at Christmas Valley, the maximum eclipse occurred around this time. And you can see that during the onset, partial phase of the eclipse, the onset, the more scatter is, less scatter is returning, and also the range of scatter seems to be increasing slightly. And it's also, the recovery period is very symmetric around totality with the onset. But when we take a look at the eastward looking radar, we don't see as symmetric or as clear of a response. We same time of totality, but you don't see much of an increase in the range of the signal, though you do see a decrease in the amount of signal around totality, but also there's a much quicker recovery. Then going to Fort Hayes West, the eclipse occurred a bit later in the day, so around here, about 1800, so I don't know if you can see the pointer. And here we can see a decrease around totality at the and a increase in slight range, at least of one of the scattering bands during the onset phase of the eclipse. But we don't see the symmetric recovery that we saw at Christmas Valley. There's something that looks like recovery several hours later, but that also appears in the Christmas Valley plots as well, so that might not be eclipse related. So, and then at Fort Hayes East in the lower left, lower right, there's almost no discernible eclipse response, and also the noise is much noisier than westward looking radar in Kansas. So, summary is that almost all the radars observed some decrease in the amount of the amount of signal returned near totality, and the signature of the eclipse is much clearer in the westward looking camping beams. However, the recovery period and even the onset period differs greatly between the two sites. Thank you for this annotation. Okay.
5 minutes, Magda.
Okay, wow, went way too slow. Okay, well, the elevation angles, as you would expect, you could see that that only lower ones are returned. And this is, I only show this because elevation angle data is helpful in our analysis, which involves ray tracing through, generating models of the eclipse ionosphere with different assumptions, and then using FARLAP to ray trace through them and ray trace through the output of the model and generate simulated radar data, which we can compare with the measured to determine the validity of the different hypotheses, and the elevations are very helpful to compare. So as you saw before, the path, the eclipse path lengthened, the signal path lengthened during the eclipse, especially at Christmas Valley, but it could have been, just looking at that, it could be either due to a change in the height of the layer or ducting through the eclipsed region. Looking at the ray trace plots in profile view, you can see that, well, so the white lines of the paths and the background is kind of plasma frequency, which is proportional to the electron density. And top is the control case and bottom is the eclipse case. And you can see that the height of the peak density in both cases is about the same, but the signals in the eclipse case are ducted in the ionosphere to a greater distance. and also more of them escape. So this path lengthening was due to ducting and not changing in layer height according to our model. And I'm gonna get this quick because I only have a few minutes left, but this is just an example of how we can use this ray trace analysis to compare, to improve our models. So this shows the elevation angles at Christmas Valley West data at the top, and then one of our eclipse masking functions model output in B, which has much higher elevation angles than the data, and then an improved one in the bottom panel, which has elevation angles that for Transcata that actually much closer to those observed. And I don't think I have time to go into this, but my presentation is going to be online. But one of the reasons one among many reasons that we might see differences between the Christmas Valley and Fort Hays data is due to the differences in the magnetic field orientation at each site. And also, we did a study that involved changing the direction of the neutral wind in this in our model and seeing how that would impact the electron density and then the ray trace. And we can see that the components that are best aligned with magnetic field have the most impact on the radar data, the simulated data. So this is just a summary, but one thing got out of this is that these SAMI model and far left ray tracer can be used together to better understand eclipse dynamics. And well, we have another one coming up soon, so more data from the SuperDARN and the HAM community and other sources could help us answer some of the remaining unanswered questions. And with that, let's open the questions of the next speaker.
Thank you so much, Magda. Do we have any questions?
Just one quick question. I missed something. What does the term camping beam mean? Why do you call it that?
We call it it's kind of like the base. So it's SuperDARN's kind of scanning across. SuperDARN's kind of scanning across the field of view, going from one to the next. Except in between motion, like in between successive beams, it returns to the camping beam. So it's kind of its base. It scans one beam, then goes and takes a measurement along camping beam. Scans a different beam, goes back to the camping beam, makes a measurement. So that's why it's camping. It's
okay, okay, I got it. Thank you.
Great, thank you so much, Magda. I really appreciate that.